So as we talk about the oxidation of fatty acids, I want you to keep a couple things in mind. First, fatty acid oxidation is a high energy yielding process, and it can support the cellular needs during fasting and under conditions when excess energy is needed. So when is beta oxidation occurring? It's again a fasted state metabolic pathway. So this is happening when glucagon is high and insulin is low. So just as a quick reminder, in the fasted state, it's going to be our liver and our skeletal muscle that are primarily going to oxidize free fatty acids in the process of beta oxidation to produce energy. And what we'll see is these free fatty acids come from the process of lipolysis, which is important for the freeing of stored triacylglycerols. But for now, let's just look at the process of how we use free fatty acids to generate ATP. So when free fatty acids are taken up into the liver or the skeletal muscle, they need to be transported into the mitochondria because this is where the process of beta oxidation occurs. Initially, these free fatty acids are activated to acyl-CoA derivatives, or a fatty acyl-CoA. And these CoAs can be transported across the outer mitochondrial membrane using the transporter carnitine palmitoyltransferase 1. From here, the fatty acyl group will be transferred onto carnitine to generate an acylcarnitine. And this acylcarnitine can then be transported into the mitochondria as an acylcarnitine. The carnitine can be recycled back into the intermembrane space, and our fatty acyl-CoA can undergo the process of beta oxidation. So our two transporters needed to get free fatty acids from the cytosol into the mitochondria are carnitine palmitoyltransferase 1 and carnitine palmitoyltransferase 2. Of note, this process requires the cofactor carnitine, which can be recycled in this process. So if we look more closely at fatty acid beta oxidation, this is the process we just discussed here. Our fatty acid comes in, it generates a fatty acyl-CoA on the cytosolic side and is transported through both mitochondrial membranes, and the resulting fatty acyl-CoA is now in the mitochondria and ready for beta oxidation. So the process of beta oxidation is summarized here, and it essentially involves a series of 4 enzymes that preferentially oxidize different length fatty acids. The full beta oxidation spiral, as shown here, consists of 4 steps: a dehydrogenase, a hydrolase, another dehydrogenase, and a thiolase. What's most important about this process are the products of beta oxidation, and those products are NADH, FADH2, and acetyl-CoA. So for each turn of the beta oxidation spiral from a long-chain fatty acid, you'll produce 1 FADH2, 1 NADH, and 1 acetyl-CoA. The NADH and FADH2 generated will be oxidized in the electron transport chain to produce ATP. The acetyl-CoA will be used in the process of ketogenesis. The only exception to this pathway is the oxidation of odd-chain fatty acids that will result in the generation of propionyl-CoA as a final carbon unit, and that can be oxidized in the TCA cycle. So beta oxidation is primarily regulated at the level of the transport of long-chain fatty acids across the mitochondrial membrane. Cytosolic levels of malonyl-CoA will inhibit carnitine palmitoyltransferase 1 and therefore ensure that beta oxidation is not occurring at the same time as fatty acid synthesis. We'll look at fatty acid synthesis more closely, but this process is a cytosolic process that starts with the production of malonyl-CoA. So if malonyl-CoA is elevated in the cytosol, it's an indicator that fatty acid synthesis is also occurring. So as I mentioned, in addition to the regulation, the most important point of beta oxidation are the products produced. So what are those products again? NADH and FADH2, as well as acetyl-CoA. The NADH and FADH2 are used in the electron transport chain to produce ATP, while the acetyl-CoA is a substrate for ketogenesis, and if you remember, it also allosterically activates pyruvate carboxylase, which is an enzyme needed for gluconeogenesis. We also want to keep in mind that the ATP produced from this process in the fasted state is required for anabolic processes, and those processes are gluconeogenesis and the urea cycle. So beta oxidation is highly supportive of both these two processes in fasted state metabolism because of its ability to produce high levels of ATP.